There's a hole in the universe, not a black hole, not a region of unusually low star formation, not a gap in a catalog caused by an instrument limitation or an observational blind spot, an actual hole. A spherical region of space approximately 1 billion light years across, containing almost no galaxies, no star clusters, no gas clouds dense enough to form stars, no significant concentrations of dark matter, no structure of any meaningful kind, just empty space, stretching in every direction for a distance so vast that if you traveled through it at the speed of light, the fastest speed at which anything in the universe can move, the journey from one side to the other would take 1 billion years. It is called the Boötes Void, and it should not exist, not in the way that unusual things sometimes should not exist, where we mean they are surprising or rare or statistically unlikely, in the more precise sense. In the sense that the best models of how the universe formed and evolved from the Big Bang to the present day do not easily produce structures of this size and this emptiness. The mathematics of cosmology, the equations that describe how matter clumped and clustered under gravity across 14 billion years of cosmic history, struggle to account for something this large being this empty. Astronomers who study the large-scale structure of the universe have a word for regions like this. They call them voids, and voids are not unusual. The universe is full of them, vast bubbles of near-empty space surrounded by the filaments and walls and clusters of the cosmic web, the sponge-like structure that defines the architecture of matter on the largest scales. Voids are a natural and predicted consequence of the way structure forms in the universe. They were there in the early universe as slight underdensities, regions where matter was marginally less concentrated than average, and they grew over billions of years as gravity pulled matter away from them toward the surrounding filaments, leaving them progressively emptier as everything else became progressively denser. Cosmologists expected voids, they predicted them. They found them and cataloged them, and the existence of voids in general does not trouble the standard model of cosmology in any significant way. What troubles the standard model is the Boötes void specifically, because the voids that cosmological models predict, the voids that the mathematics of structure formation naturally produces, are not 1 billion light years across. They are tens of millions of light years across, a few 100 million at the very most in extreme cases. Large enough to be significant features of the cosmic web, not large enough to make the people who found them go quiet in a conference room in 1981 and spend the next 4 decades trying to work out what they were looking at. The Boötes void is not a large void. It is a void in a category of its own. The discovery happened the way many of the most important discoveries in science happen, not through a targeted search for something expected, but through a survey of something routine that produced a result nobody was prepared for. In 1981, a team of astronomers led by Robert Kirshner at the Harvard-Smithsonian Center for Astrophysics was conducting a survey of galaxy redshifts in the direction of the constellation Boötes. Redshift surveys are one of the fundamental tools of cosmology. By measuring how much the light from distant galaxies has been stretched toward the red end of the spectrum by the expansion of the universe, astronomers can calculate how far away those galaxies are and use that information to build three-dimensional maps of how matter is distributed across space. The survey was methodical, systematic. the kind of careful observational work that produces data rather than drama. And then the data came back. In the direction of Boötes, across a range of distances corresponding to a region of space roughly 1 billion light years across, the survey found almost nothing. Galaxy after galaxy at the distances surrounding this region, dense clusters, filaments, the familiar architecture of the cosmic web visible in every other direction the survey examined. And then, in this specific volume of space, a near complete absence. Not zero galaxies. A void of this size will always contain some galaxies, scattered thinly across its interior, outliers that ended up inside the emptiness rather than clustering on its walls. But the number of galaxies found inside the Boötes Void was so far below what any cosmological model predicted for a region of that size that the deficit was immediately, unmistakably significant. Kirshner and his colleagues published their results. The paper described what they had found with the measured understatement that characterizes good scientific writing. An unusually large void, an underdensity of remarkable extent, a structure that would require explanation within the framework of cosmological models. What the paper could not quite convey, what the language of scientific publication is not designed to convey, was the simple, immediate, visceral strangeness of the thing they had found. If this is the kind of content you want more of, subscribing to The Cosmic Depth takes 2 seconds. And we post new documentaries every few days. Because the Boötes Void is not strange in the way that black holes are strange. Objects so extreme that their strangeness requires advanced physics to appreciate. It is strange in a more immediate way. In a way that requires nothing more than the ability to look at a number and feel its weight. 1 billion light years, across, empty. To put that in terms that carry some of the right emotional weight, consider this: the Milky Way galaxy. Your galaxy, the galaxy that contains every star you have ever seen in the night sky, every planet we have ever visited with a spacecraft, every place in the universe where human beings have ever pointed an instrument, is approximately 100,000 light years across. The Boötes Void could contain 10,000 Milky Way galaxies laid end to end across its diameter. It could contain the entire observable neighborhood of our galaxy, everything within 500 million light years of Earth, and still have room. If our galaxy were located inside the Boötes Void rather than in the populated region of the cosmic web where it actually sits, the night sky would look different in a specific and profound way, not darker. Individual stars within our galaxy would look the same. But the smudges of light that represent other galaxies, the ones visible to the naked eye on a clear night, the ones that fill the deep field images from the Hubble and James Webb telescopes, would be gone. Or rather, they would be there, but so distant, so far beyond the boundary of the void, that for most of human history, our instruments would not have been sensitive enough to detect them. If we lived inside the Boötes Void, we might have looked up at the night sky for most of our history and concluded, reasonably if incorrectly, that the Milky Way was the universe, that there was nothing else, that the darkness surrounding us was not the darkness between galaxies, but simply the darkness of infinite empty space with no content. We would have been wrong, but we might not have known we were wrong until very recently. The Boötes Void is, in this sense, a reminder of something important about the relationship between observation and knowledge. What we know about the universe is always constrained by where we are and what we can see from there. Our galaxy sits in a populated region of the cosmic web, and we can see the structure of the universe around us, the filaments and clusters and voids, because we have enough nearby reference points to map it. The void reminds us that this is a local condition, not a universal one, that our particular position in the cosmic web, our particular neighborhood, gives us a view that other positions would not. Understanding what the Boötes Void actually is, why it exists, how it formed, what it tells us about the physics of the universe on the largest scales, requires understanding what the universe is supposed to look like. And the universe is supposed to look nothing like this. The universe has a shape, not a shape in the simple sense, not a sphere or a cube or any geometric form that has a name in ordinary language. A shape in the sense that matter, distributed across billions of light years of space, is not distributed randomly. It has structure, pattern, architecture that emerged from the earliest moments of cosmic history and has been developing, growing more elaborate and more defined across 14 billion years of gravitational evolution. That structure has a name: the cosmic web. To understand why the Boötes Void is so difficult to explain, you first need to understand what the universe looks like when it is working normally. When matter is distributed the way the physics of structure formation predicts it should be. When the 14 billion year history of gravity pulling things together and dark energy pushing things apart has produced the architecture it is supposed to produce. The cosmic web looks like a sponge, or more precisely, like the three-dimensional skeleton of a sponge. Vast sheets and filaments of matter stretching across hundreds of millions of light years, forming the walls and threads of an interconnected network. At the intersections of these filaments, where multiple threads of matter converge, sit the densest regions of the universe, galaxy clusters, concentrations of hundreds or thousands of galaxies bound together by gravity, surrounded by the hot gas that fills the space between them, anchored in place by enormous halos of dark matter that extend far beyond the visible galaxies themselves. Along the filaments themselves, between the clusters, galaxies are strung like beads, distributed along the threads of the web in elongated structures, sometimes called galaxy walls or galaxy chains. Moving along these filaments under the influence of gravity, slowly falling toward the nearest cluster, taking billions of years to travel distances that light covers in millions. And between the filaments, in the spaces enclosed by the web, the voids, bubbles of near-empty space. Regions from which matter has been drawn away over billions of years as gravity pulled it toward the surrounding filaments and clusters, leaving behind an underdensity that grows progressively emptier as the universe ages. The voids are not completely empty. They contain galaxies scattered thinly across their interiors, the outliers that ended up on the wrong side of the gravitational divide and spent the age of the universe slowly drifting toward the void walls rather than falling toward a cluster. But they are substantially emptier than the average density of the universe. Regions where matter took a different path. This structure, the cosmic web of filaments and clusters and voids, is one of the great confirmations of modern cosmology. The simulations that cosmologists run on supercomputers, starting from the initial conditions of the universe as measured by the cosmic microwave background and running forward 14 billion years under the known laws of physics, produce a cosmic web that matches the observed large-scale structure of the universe with extraordinary precision. The filaments are in the right places. The clusters have the right masses. The voids have roughly the right sizes. Roughly, because this is where the Boötes Void begins to cause problems. The voids that the simulations produce, the voids that the standard model of cosmology naturally generates through 14 billion years of structure formation, are not 1 billion light years across. The largest voids in the standard cosmological simulations are typically in the range of 300 to 400 million light years across. In exceptional cases, the very largest structures that the models produce at the tail end of the size distribution, perhaps 500 million light years. These are genuine giants of the cosmic web, structures that would take light hundreds of millions of years to cross. Features that dominate the visual appearance of the large-scale universe when you map the distribution of galaxies across hundreds of millions of light years. The Boötes Void is 1 billion light years across. It is roughly 2 to 3 times larger than the largest voids that standard cosmological models comfortably produce. This discrepancy is not a rounding error. It is not a measurement uncertainty that better data will resolve. It is a genuine puzzle. A feature of the observed universe that sits in tension with the best theoretical framework we have for understanding how the universe formed and why it looks the way it does. To understand why size matters so much here, why the difference between 500 million light years and 1 billion light years is qualitatively important rather than just quantitatively larger, you need to understand something about how voids grow. Voids grow through a process that cosmologists call void expansion. In the early universe, in the period after the Big Bang when matter was distributed nearly uniformly across space, there were tiny fluctuations in density. Some regions were very slightly denser than average. Others were very slightly less dense. These fluctuations were not large. They were of the order of 1 part in 100,000, barely detectable in the cosmic microwave background radiation that is the afterglow of the Big Bang. But they were enough. Gravity amplified them. Regions that were slightly denser attracted more matter, becoming denser still. Regions that were slightly less dense lost matter to their denser surroundings, becoming emptier still. Over hundreds of millions and billions of years, this process, the gravitational amplification of tiny initial fluctuations, transformed the nearly uniform early universe into the structured cosmic web we observe today. The voids formed and grew as matter flowed away from underdense regions toward overdense ones. The rate at which they grew was determined by the amplitude of the initial density fluctuations, the amount of dark matter available to drive the gravitational collapse, and the competing influence of dark energy. The mysterious component of the universe that is driving the accelerating expansion of space, and that acts to counteract the gravitational collapse of structure on the largest scales. All of these factors are known, they are measured, they are constrained by observations of the cosmic microwave background, the distribution of galaxies, the expansion history of the universe as measured by distant supernovae. The standard model of cosmology, lambda CDM, as it is formally known, for the cosmological constant and cold dark matter that it is built around, incorporates all of them. And when you run that model forward for 14 billion years and look at the voids it produces, none of them are as large as the Boötes Void. The question this raises is the most important question in the science of the Boötes Void. Is the model wrong? Or is the Boötes Void a statistical outlier, an extremely rare but technically possible feature of the universe that the model can produce? Just not often, just not typically, just not in the overwhelming majority of simulated universes. An object that sits at the very extreme tail of the distribution of possible structures, rare enough that finding one in our observable universe is surprising but not impossible. This is the tension that has defined the scientific discussion of the Boötes Void for 4 decades. It is not a tension that has been resolved. It is not a case where one side of the argument has clearly won. On one side, the argument that the Boötes Void, while extreme, is within the statistical range of what the standard model can produce. That the observable universe is large enough and the distribution of void sizes broad enough that finding one structure this anomalous is not enough to reject the model. That science requires more than one anomaly before it abandons a framework that has been confirmed by so many other observations. On the other side, the argument that the Boötes Void is large enough and the tension with the standard model significant enough that it deserves to be taken seriously as a potential signal that something is missing from our cosmological framework. That the models do not merely fail to predict structures this large frequently, they fail to predict them at all in the vast majority of simulated universes. And that a model which requires you to be extremely lucky to explain a major observed feature of the universe is a model that deserves scrutiny. Neither argument is unreasonable. Both are held by serious scientists working with the same data. What makes this genuinely interesting, rather than merely technically contested, is what each side of the argument implies about the universe. If the standard model is essentially correct, and the Boötes Void is a statistical outlier, an extreme but explicable feature, then we live in an unusual region of an otherwise well-understood cosmos. Our observable universe happened to contain one of the largest voids that the physics of structure formation can produce. We are, in this reading, cosmologically lucky, or unlucky, depending on how you think about it. If the standard model is incomplete, if the Boötes Void is a signal that something is missing from our understanding of how structure forms and grows in the universe, then the implications reach further. They touch the physics of dark energy, which is the dominant factor controlling the growth of structure on the largest scales. They touch the initial conditions of the universe, the precise spectrum of density fluctuations in the early universe from which all structure ultimately grew. They touch the question of whether there are additional physical processes operating on the largest scales of the universe that our current models do not include. A void 1 billion light years across is, in this reading, not just a large empty region of space. It is a diagnostic, a probe of the physics that operates on scales so large that no other observation can reach them. A feature of the universe that is, in principle, sensitive to things that smaller structures cannot measure. To the properties of dark energy, to the statistics of the initial fluctuations, to whether the standard model of cosmology is the complete story, are only a very good approximation to something more complicated. The Boötes Void is large enough and anomalous enough that these questions are not merely academic. They are live scientific debates with real implications for how we understand the universe we live in, and the answers have not yet been found, which is partly because the explanations that have been proposed, the serious, carefully developed scientific attempts to account for a void this large in a universe governed by known physics, each run into difficulties of their own. Science does not leave anomalies alone. When something appears in the data that does not fit the models, when an observation sits in tension with the best theoretical framework available, the response of science is not to ignore it, and not, at least not immediately, to abandon the framework. The response is to ask whether the observation can be explained within the existing framework through some mechanism that has not yet been fully considered. For the Boötes Void, several such mechanisms have been proposed. Each of them is serious. Each has been developed by careful scientists working with real mathematics and real physics. And each, when you follow it carefully to the end, runs into a problem that leaves the mystery not quite resolved. The first and most straightforward explanation is that the Boötes Void is not as anomalous as it looks. This sounds like avoiding the question, but it is actually a precise scientific argument. It goes like this. The standard model of cosmology predicts a distribution of void sizes, a range of how large voids can be, with smaller voids being common and larger voids being progressively rarer. The Boötes void, in this argument, sits at the extreme tail of that distribution. It is rare, very rare, but rare is not the same as impossible. The observable universe contains a large number of voids. If you have enough voids, even the tail of the distribution gets sampled. Finding one very large void in the observable universe is, in this argument, not a signal that the model is wrong. It is a signal that you have a large enough sample to find rare events. This explanation is technically valid. The statistics work in principle. The problem is in the details. When cosmologists run simulations of the universe using the standard model, large box simulations that generate synthetic universes with the same initial conditions and the same physics as our own, and then look for voids as large and as empty as the Boötes void, they find them only very rarely. In some simulations, the probability of producing a void, this anomalous in an observable universe of our size, is estimated at a few percent. In others, the probability is considerably lower. A few percent is not zero. A few percent means it can happen. But a few percent also means that if you ran the universe 100 times with the same initial conditions and the same physics, the overwhelming majority of those universes would not contain a Boötes void equivalent. We appear to live in one of the unusual ones, which is either reassuring, we got lucky, or suspicious. Why did we get lucky? Depending on how seriously you take the anthropic argument that observers necessarily find themselves in universes capable of producing observers, which does not obviously select for enormous voids. The second explanation focuses on the initial conditions of the universe, the specific pattern of density fluctuations in the early universe from which all subsequent structure grew. The cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe, encodes a map of those initial density fluctuations. Cosmologists have measured this map with extraordinary precision using satellites like COBE, WMAP, and Planck. The pattern of fluctuations they found is broadly consistent with the predictions of inflation, the theory that the very early universe underwent a brief period of exponential expansion that stretched quantum fluctuations to cosmic scales and produced the nearly uniform but subtly varied initial conditions from which the cosmic web eventually grew. The key word is broadly. The cosmic microwave background map contains some features: anomalies in the statistical distribution of the fluctuations, unexpected alignments of structures on large scales, a so-called cold spot in the southern hemisphere that has been tentatively linked to the influence of a supervoid, that do not fit perfectly with the simplest inflationary models. These anomalies are individually not significant enough to reject the framework, but they suggest that the initial conditions of the universe may have been slightly different from the simplest prediction, that the spectrum of fluctuations may have had features that drove the formation of unusually large structures in certain regions of the universe. In this argument, the Boötes void is not a product of unusual dynamics during the 14 billion years of structure formation. It is a product of unusual initial conditions at the very beginning, a region of the early universe that was particularly underdense from the start, seeded by a fluctuation that was larger than typical, producing a void that grew over billions of years to a size that typical fluctuations would not have reached. This is a plausible argument. It connects the Boötes void to a broader set of large-scale anomalies in the cosmic microwave background that suggest the universe's initial conditions may be more complex than the simplest models predict. It does not require new physics in the late universe, only a more complex inflationary scenario in the early one. The problem is that it is not directly testable in any clean way. The initial conditions of the universe are fixed. We cannot run the universe again with different initial conditions and see if the Boötes void still forms. We can look for correlations between the Boötes void and anomalies in the cosmic microwave background map. And some researchers have done exactly this, finding tentative but not conclusive connections. But the evidence remains indirect, and the argument remains suggestive rather than established. The third explanation is the one that has attracted perhaps the most attention in the cosmological literature: the idea that the Boötes void is not a single void at all. It is several voids merged into one. Void merging is a real process in cosmological structure formation. As the universe evolves and voids grow, neighboring voids can expand until they touch, until the filament or wall separating them becomes thin enough that it effectively dissolves, the matter in it falling away to the surrounding clusters, and the two voids merging into a single, larger structure. This process, sometimes called void merging or void coalescence, can produce voids significantly larger than any individual void that forms in isolation. The argument for the Boötes void being a merged supervoid is supported by some observational evidence. Surveys of the galaxy distribution around and within the void have found hints of internal structure. Slight variations in the galaxy density across different regions of the void's interior that could represent the remnants of the walls and filaments that once separated multiple smaller voids before they merged. If this internal structure is real, if the Boötes void contains within it the fossil record of its own formation through merging. It would support the idea that the void grew to its current size through accumulation rather than through a single period of expansion. The problem is that even void merging has limits. When cosmologists model void merging in simulations and ask how large a merged supervoid can realistically become, how many voids of what sizes would need to merge to produce a structure 1 billion light years across? The numbers become difficult to reconcile with the standard model. Producing a merged void of this size requires either an unusually large number of merging events or unusually large individual voids merging together, or both. And in each case, you run back into the original problem. The standard model does not easily produce the ingredients needed to build a Boötes void by merging. The merged void hypothesis moves the problem rather than solving it. The fourth explanation invokes dark energy more directly. Dark energy, the mysterious component of the universe responsible for the accelerating expansion of space, is not merely a background phenomenon. It actively influences the growth of structure. In regions of space where the local density of matter is lower than average, in voids, the gravitational forces that would otherwise slow the expansion are weaker, and dark energy drives the expansion of the void more effectively than it does in denser regions. Some theoretical models of dark energy, models more complex than the simple cosmological constant that the standard model uses, produce different rates of void growth in different environments. If dark energy is not a constant, but a dynamical field, a quintessence field, or something similar, its properties might vary across space in ways that accelerate the growth of voids beyond what the standard model predicts. In this argument, the Boötes void is a diagnostic of dark energy properties on the largest scales. It is telling us not just that a large void exists, but that dark energy, still one of the least understood components of the universe, may behave differently from what we assume. This is a genuinely interesting possibility. Dark energy is known only through its gravitational effects. Through the accelerating expansion of the universe, and through the suppression of structure growth it causes on the largest scales. Any observation that is sensitive to the properties of dark energy in a way that existing measurements are not is potentially valuable. The Boötes void, if its size is genuinely in tension with standard dark energy models, could be providing exactly that kind of new information. The problem is that distinguishing between different dark energy models using void statistics requires much better measurements of void properties than we currently have. Better maps of the galaxy distribution within and around the void, better measurements of how empty the void actually is, better constraints on whether the void's size is as anomalous as current data suggest. Some of these measurements will improve with the next generation of large galaxy surveys. Instruments like Euclid and the Vera Rubin Observatory, currently coming online, that will map the distribution of hundreds of millions of galaxies across the observable universe with unprecedented precision. But the measurements do not yet exist in the form needed to test these dark energy models conclusively. So we wait and look, and the void remains unexplained. What strikes me most about this catalog of explanations, the statistical outlier argument, the unusual initial conditions argument, the void merging argument, the dark energy argument, is not that none of them is conclusively right. Science rarely produces instant, conclusive resolutions to genuine mysteries. What strikes me is that each of them, if it turned out to be correct, would be significant. If the Boötes Void is a statistical outlier, we live in an unusual universe, one that sits at the extreme end of what the standard model can produce. That is worth knowing. If it reflects unusual initial conditions, the inflationary model that produced those conditions is more complex than its simplest form. And understanding that complexity would teach us something fundamental about the first fractions of a second of cosmic history. That is worth knowing. If it formed through void merging on a scale the standard model struggles to produce, there is something about the dynamics of large-scale structure formation that our simulations are not capturing correctly. That is worth knowing. If it is a signature of dark energy behaving differently from a simple cosmological constant, the most mysterious component of the universe is stranger than we thought. That is worth knowing. The Boötes Void is not merely a large, empty region of space. It is a question, a billion light-year question, phrased in the language of absence rather than presence, sitting in the constellation Boötes and waiting for an answer that the cosmology of the early 21st century has not yet been able to provide. The next generation of surveys will gather more data, better maps of the galaxy distribution, more precise measurements of the void's properties, stronger constraints on what the standard model can and cannot produce. The Euclid Space Telescope and the Vera Rubin Observatory will between them map the distribution of galaxies across the observable universe with a precision that makes current surveys look preliminary. Whether that data will resolve the mystery of the Boötes Void or deepen it remains to be seen. Both outcomes are scientifically valuable, and both, in their different ways, will teach us something about the universe we did not know before. Stand at the edge of the Boötes Void, not literally, not in any physical sense that could ever be realized in a human lifetime or 1,000 human lifetimes, but in the way that science allows, in the way that mathematics and observation and the careful accumulation of data make it possible to stand somewhere in your mind that your body could never reach. Stand at the edge of the Boötes Void and look inward. What you would see, what the physics tells us you would see if you could somehow be transported to one of the thin scattering of galaxies that populate the void's interior, is a sky unlike any sky that has ever been seen by any mind in our corner of the universe. Not darker, not visually different in any dramatic way at the scale of individual stars. The stars of your own galaxy would look the same, close, familiar, distributed across the sky in the patterns that gravity and the geometry of the galactic disk produce. The Milky Way's band would still stretch overhead. The nearest star systems would still be within reach of light, their light arriving over years or decades or centuries in the way it does from here. But look further. Look past the immediate neighborhood. Look to the distances where, from our actual position in the populated region of the cosmic web, you can see the smudges of other galaxies. The Andromeda Galaxy visible to the naked eye on a clear night, the Virgo cluster visible with modest telescopes, the rich fields of distant galaxies visible in the deep exposures of the Hubble and James Webb Space Telescopes. From inside the Boötes Void, those smudges would be absent, or rather, they would be there eventually at the edge of the void and beyond it, at distances so much greater than those we are accustomed to thinking of as the scale of the visible universe. But for most of human history, for all of human history before the most powerful telescopes of the late 20th century were built, those distances would have been beyond reach, beyond detection, beyond any instrument that human ingenuity could have constructed in any era before the present one. If our galaxy were inside the Boötes Void, the nearest external galaxy to us, sitting on the void's boundary rather than in our actual neighborhood, would be at a distance of several 100 million light years. Compare that to Andromeda, our nearest large galactic neighbor, which sits at approximately 2.5 million light years. From inside the void, the nearest equivalent of Andromeda would be 200 times further away. Its apparent brightness, which falls off as the square of the distance, would be 40,000 times fainter. Invisible to the naked eye, invisible to early telescopes, invisible to anything but the most powerful instruments of modern astronomy. And here is the thought that sits with me when I consider this. For the majority of human history, for all of the centuries during which human beings looked up at the night sky and wondered what it meant, the answer to the question of what exists beyond our galaxy was simply unknown. The existence of other galaxies was not confirmed until 1924, when Edwin Hubble used the Cepheid variable stars in Andromeda to establish that it was a separate stellar system far beyond the boundaries of the Milky Way. Before that, for the entire prior history of astronomical observation going back thousands of years, the nature of the nebulae visible in telescopes was debated but unresolved. Were they gas clouds within our galaxy or island universes beyond it? The question was answerable eventually, because Andromeda is close enough that its individual stars could be resolved with the instruments Hubble had access to. If our galaxy were inside the Boötes Void, that question might not have been answerable until decades later, perhaps much later, perhaps not until space telescopes were available. The confirmation that the universe contains other galaxies, a fact that is now so fundamental to our understanding of cosmology that it is taught in schools, a fact that underlies every subsequent discovery about the large-scale structure of the universe, might have arrived in our understanding much more recently than it did. Or it might not have arrived at all. It is conceivable, not certain, but genuinely conceivable, that a civilization located inside the Boötes Void, developing its science and its technology on a timeline similar to ours, would have reached a level of astronomical sophistication comparable to early 20th century Earth, while still being unaware that the universe contained structures beyond its own galaxy. That is a profound thought. Not because it changes anything about the actual structure of the universe. The Boötes Void would still be there. The cosmic web surrounding it would still be there. The other galaxies would still exist at their actual distances, regardless of whether any mind within the void was aware of them. But because it reveals something important about the relationship between position and knowledge, about how much of what we know about the universe is a consequence of where we happen to be within it. We know the universe is vast and structured and full of galaxies because we are in a position to observe it. Because our galaxy sits in a populated region of the cosmic web where the nearest large galaxies are close enough to have been detected by instruments available a century ago. Because our location gave us the observational leverage to discover the large scale structure of the universe early in the development of our astronomical science. A different location would have given a different view. A different view would have produced different discoveries. A different sequence of discoveries would have built a different understanding of what exists. Knowledge is not independent of position. This is true in physics. We have known since Einstein that what you observe depends on where you are and how you are moving. But the Boötes Void makes it true in a broader and more immediate sense. The civilization inside the void and the civilization outside it would observe different universes. Not different in the sense of physically different. The same laws, the same matter, the same large-scale structure. Different in the sense of differently accessible. Different in the sense of what the instruments available at any given stage of technological development can reach. We are fortunate to be where we are. Not fortunate in the sense of having been chosen or placed. The Milky Way's position in the cosmic web is a consequence of the same gravitational dynamics that placed every other galaxy where it is. But fortunate in the sense that our position gives us a view of the universe that is rich in information, dense in reference points, full of nearby objects that have allowed us to calibrate our instruments and develop our cosmological understanding in ways that a more isolated position might not have permitted. The Boötes Void, seen from the outside, is a feature of the cosmic web, a vast underdensity surrounded by the sheets and filaments of galaxies that define its boundary. Seen from the inside, it would be a different kind of universe entirely. Now, look at the boundary itself. The galaxies that ring the Boötes Void, that populate its walls and the filaments surrounding it, are not randomly distributed. They are organized into some of the largest structures in the observable universe. The CFA2 Great Wall, a sheet of galaxies stretching across approximately 500 million light-years, one of the first large-scale structures of the cosmic web to be identified and mapped, runs along part of the void's boundary. Other clusters and filaments surround it on different sides, their own internal dynamics shaped in part by the presence of the vast underdensity at their interior edge. This is a pattern that appears throughout the cosmic web. Voids are not merely negative spaces, empty regions between the structures that matter. They are active participants in the dynamics of the cosmic web. The expansion of a void, the flow of matter away from its interior toward its walls, contributes to the growth and density of the filaments and clusters that surround it. The void and its boundary are not separate things. They are a single system, the emptiness and the structure defining each other through the gravitational dynamics that connect them. The Boötes Void, in this sense, is not just a hole, it is an engine, a region of space whose expansion over billions of years has been driving matter toward its walls, compressing and organizing the structures that surround it, contributing to the density of the filaments and clusters that make the cosmic web what it is in our region of the universe. The galaxies on the boundary of the Boötes Void exist where they are partly because of the void. The void exists where it is partly because of the overdensities that surround it. The structure and the emptiness are inseparable, two aspects of the same large-scale gravitational evolution the same process of differentiation that has been transforming the nearly uniform early universe into the highly structured cosmos we observe today. To see the Boötes Void as simply an absence, a region where something is missing, is to misread it. It is a presence of emptiness on a scale that nothing in our everyday experience can calibrate, a presence that has been shaping the region of the universe around it for billions of years, a presence that sits at the boundary of what our best cosmological models can explain and asks questions that those models have not yet fully answered. There is a version of the universe in which the Boötes Void is unremarkable, a universe in which the standard model of cosmology produces structures of this size routinely, in which a billion light-year void is simply a large but expected feature of the cosmic web, the kind of thing that appears in simulations frequently enough that finding one in the observable universe requires no special explanation. We do not appear to live in that universe. Or, if we do, if the standard model is correct and the Boötes void is simply a statistical outlier that the model can technically produce, then we live in an unusual instance of it. A realization of the standard model that sits at the extreme end of what the physics allows. A universe that is, by the standards of its own governing equations, atypical. Both possibilities are worth sitting with, because both of them say something important about where we are and what we are looking at when we look out at the large-scale structure of the cosmos. The Vera Rubin Observatory in Chile, named for the astronomer whose work on galaxy rotation curves provided some of the first compelling evidence for the existence of dark matter, began operations in the mid-2020s. Its legacy, Survey of Space and Time, will spend 10 years photographing the entire visible southern sky every 3 nights, mapping the distribution of billions of galaxies across the observable universe with a precision and completeness that makes every previous galaxy survey look like a preliminary sketch. For the science of the Boötes void specifically, the Rubin Observatory's data will matter in several ways. It will produce better maps of the galaxy distribution within and immediately surrounding the void. Maps detailed enough to test the void merging hypothesis, to look for the internal structure that would betray a history of multiple voids coalescing into one. It will provide much better statistics on the overall population of voids in the universe, the distribution of sizes and shapes and emptiness levels that will allow cosmologists to test whether the Boötes void is genuinely anomalous by the standards of the model, or whether the model's predictions for the largest voids have been underestimated. And it will contribute to the measurement of dark energy properties on large scales, the kind of measurement that might eventually reveal whether the accelerating expansion of the universe is driven by a simple cosmological constant, or by something more dynamic whose effects differ from place to place. The Euclid Space Telescope, launched in 2023, and now mapping the 3-dimensional distribution of galaxies across 10 billion light-years of cosmic history, is complementary in its approach. Where the Rubin Observatory surveys wide and deep in the local universe, Euclid reaches further back in cosmic time, mapping how the cosmic web evolved across billions of years of expansion. The combination of the two surveys will provide a picture of large-scale structure, including the statistics of voids, that was not available when the Boötes void was first discovered and is not yet fully available now. These instruments will not resolve the mystery of the Boötes Void next year or the year after. Science at this scale moves slowly. The data takes years to collect and years more to analyze and interpret. The theoretical frameworks that will make sense of the data are still being developed. The argument about what the Boötes Void means for our cosmological models will continue for a long time. But the tools are better than they have ever been. And the question is being asked more seriously than it has ever been asked, because the Boötes Void is not alone. In the decades since its discovery, surveys of large-scale structure have revealed other large voids. Structures that, while not individually as extreme as the Boötes Void, collectively suggest that the universe's void population may be richer and more varied than early models predicted. The SDSS Great Wall, the KBC void, a proposed enormous underdensity centered near our own position in the cosmic web, hundreds of millions of light years across, that some cosmologists have argued is responsible for certain anomalies in the local measurement of the universe's expansion rate. The cold spot supervoid in the southern hemisphere, a region of the cosmic microwave background that is slightly cooler than the surrounding sky and that corresponds, at least roughly, to a large underdensity in the galaxy distribution. None of these is as extreme as the Boötes Void. None produces the same level of tension with the standard model individually. But together, they form a pattern, a suggestion that the universe's largest structures, both in overdensity and underdensity, may be somewhat more extreme than the simplest versions of the standard model predict. This pattern does not require a revolution in cosmology. It does not demand the abandonment of the standard model or the introduction of entirely new physics. But it does suggest that the standard model, extraordinarily successful as it is at accounting for the observable universe across most scales, may be missing something at the very largest scales. Some physical process, some complexity in the initial conditions, some behavior of dark energy that deviates subtly from a simple constant. Something that, when included in the models, would bring the predicted distribution of large structures into better agreement with what we actually observe. What that something is, nobody yet knows. And the Boötes Void sits at the center of the question, a billion light-year argument for paying closer attention to the parts of the universe that are not there. A billion light-year reminder that absence can be as informative as presence, that what the universe lacks in a given region tells you something about the physics that shaped it, something about the initial conditions, the dynamics, the properties of the dark components that dominate the universe's mass-energy budget, and that we understand least well. The cosmic web is usually studied by looking at the filaments, at the clusters, at the dense regions where matter has concentrated and where galaxies and stars and the conditions for chemistry and biology have accumulated. This is natural. Matter is where the interesting things are, where the light comes from, where the observations are easiest to make. But the voids are half the universe, more than half by volume. The voids occupy the majority of the observable universe's total volume. The filaments and clusters and walls, the structures we study most carefully because they are brightest and most accessible, are a minority of the space. The universe is mostly emptiness, mostly void, mostly the absence of the matter that makes it visible. Studying the voids is studying the universe as it actually is, rather than as it is most conveniently observed. The Boötes Void is the largest and most anomalous void we know of. It is the universe's most extreme statement of emptiness, a region where whatever process produces voids operated at a scale and with an efficiency that the standard model struggles to match. It is a diagnostic of physics at scales that nothing else we can observe is sensitive to. It is a question mark written in the absence of a billion years of light. And it is, in the most literal sense, one of the least understood large structures in the observable universe. 40 years after its discovery, we know where it is. We know roughly how large it is. We know that it is emptier than most cosmological models comfortably predict. We know the explanations that have been proposed, and we know the problems with each of them. We do not know why it is there. We do not know whether it is telling us that our best model of the universe is slightly wrong, or very wrong, or simply unlucky. We do not know whether larger voids exist beyond the boundaries of our current surveys, whether the Boötes Void is the most extreme structure of its kind in the observable universe, or simply the most extreme one we have found so far. We do not know whether the Boötes Void is a single structure or the remnant of a merger. We do not know whether it is connected to anomalies in the cosmic microwave background that suggest something unusual about the initial conditions of our region of the universe. We do not know whether its existence is a signal from dark energy, a hint that the force driving the accelerating expansion of the cosmos is more complex and more varied than a simple constant. We know that it is there, 1 billion light years of almost nothing, sitting in the constellation Boötes, surrounded by galaxies on its walls and filaments at its boundary, slowly expanding as the universe ages and dark energy pushes its walls further apart, waiting with the patience of something that has existed for billions of years, for the instruments and the theories and the minds that will finally understand it. Those instruments are being built. Those theories are being developed. Those minds are working on it now. In observatories and universities and research institutes around the world, in papers submitted to journals and talks given at conferences and simulations run on supercomputers that model the evolution of the universe across billions of years of cosmic time. The answer is coming. Slowly, carefully, in the way that answers to the deepest questions always come, not in a single dramatic moment of revelation, but through the patient accumulation of evidence and the gradual refinement of understanding. That is the actual texture of scientific progress. And when it comes, when we finally understand why the Boötes Void is as large as it is, what physics produced it, what it is telling us about the components and initial conditions of the universe, we will look back at that 1981 survey that first found it and recognize it for what it was. Not just a data anomaly, not just an unusually empty region of space, a discovery, one of the most important discoveries in the history of cosmology. A finding that pointed quietly and persistently toward something our models were missing, something about the universe at its largest scales that the standard picture had not fully captured. The Boötes Void has been asking that question for 40 years. We are still working out the answer. And that The fact that the universe contains structures large enough and strange enough that our best science has spent 4 decades examining them without arriving at a complete explanation is not a cause for frustration. It is a cause for wonder. The universe is larger than our models, stranger than our equations, more varied in its structures and more extreme in its features than the standard picture, as good as it is, has yet fully accounted for. The Boötes Void is the universe reminding us of that in the most dramatic way available to it, by being across 1 billion light years of space, almost entirely nothing, and making that nothing one of the most important things in the sky. If this changed the way you see the empty spaces between the stars, the voids that occupy most of the universe's volume, and that we are only beginning to understand, the cosmic depth has more waiting for you. Subscribe, and I will see you in the next one.